To do kinematics motion problems, we have a range of equations, a range of kinematics formula that we're going to use. So let's just introduce those very quickly. The first is the average velocity is equal to the displacement over time. Now this actually could be written with an S. In fact, all of these could be written with an S. I'm going to use a D for distance/displacement. Technically D for distance, S, the letter S for displacement. So you could see V_av is equal to S over T. That's to say displacement over time. But velocity is a vector, so of course we need displacement, which is a vector rather than distance, just a scalar. But anyway, well, that's the first equation. Pretty straightforward. Divide your displacement over the time, and you've got your average velocity, your average speed. And again, these sort of problems, kinematics problems, often ask you for the speed that something was going. Well, okay, speed is distance over time. Velocity is displacement over time. So the equation, the letters are interchangeable there. So next one, we've got the, now V, over here we had V_av, so the average velocity or average speed. But we just have a V by itself. That's actually the final velocity. So we have the final velocity is equal to the initial velocity plus the acceleration times time. So there's another equation there. The next equation is generally given, but it's actually just a rearrangement of the second one. If we rearrange that to find A, what we're going to come out with is that A is equal to, something's up with my pen today. A is equal to the final velocity minus the initial velocity divided by time. And hopefully you can see that this is really just a rearrangement of the previous equation. These are really one and the same equation, just being rearranged to find A instead of V. All right, remember when we rearrange equations, we can take something across the other side of the equals and do the opposite to it. Well, okay, let's do that. Let's take this U that's been added on. If we took that across, it's been subtracted now, so V minus U. And this T has been multiplied by the A. If we take that across the equals, it's going to come down the bottom and be divided by T, which is what we've got in this third equation. So like I said, this third one is really just a rearrangement of the second one. Anyway, moving on, we have the V squared, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. There's the fourth equation, number 5. Possibly my favorite, I guess, of all of these, is that D is equal to UT plus half AT squared. This is a great one because actually in terms of kinematics problems, we often have, we're often starting from rest. So the object, whatever it is stationary. So this UT actually just sort of disappears from this in a lot of the cases, because if U is equal to 0, then UT is also equal to 0. So you're just adding 0. So just get rid of it, take it out of the equation. So that can be quite handy, really. And the last one, D is equal to T times the sum of U plus V over 2. So using some brackets to group some terms there. But these are essentially the equations that you're going to use for kinematics. This top one did get a little bit messy in all my scribbles, so let's just rewrite that. V equals U plus AT. If we get rid of all this other stuff around here, there we go. There are our 6 kinematics equations that we're going to be using. Now, looking at these equations, you should note that we don't see an M anywhere, and we don't see a capital F anywhere. So force is not involved, and mass is not involved either. In terms of kinematics, we're looking at describing the motion of objects in terms of final and initial velocity, the acceleration, etc. What we don't care about is the mass of the object, and we don't care about what force actually was required to get that object moving. Except, I guess, if we're talking a pen was dropped from the top of this building, well, then we've got the force of gravity acting on the object, but we're just looking at, in terms of the acceleration, 9.81 on Earth. So we're not actually using the force or the mass. Okay, kinematics is about the motion of object. How did it get moving? Really don't care. But what's its mass? Really don't care. Irrelevant, okay, in terms of kinematics. So let's have a look at using these equations to do some kinematics motion problems. What change in velocity do astronauts experience in a rocket that accelerates upwards at 21.3 meters per second squared for a time period of 5.35 seconds? Well, we're looking for the change of velocity. The way to say change is a triangle. That's a capital delta. That means change. So we're looking for change in velocity, delta V. So the change in velocity will be the final velocity minus the initial velocity. So we're going to choose a kinematics equation that has this V minus U in it. And the one that jumps out is A is equal to V minus U over T. So there's our first step. We've chosen an equation to use. Second step would be to rearrange the equation if you need to, and in this case we do. So this implies that V minus U, or the change in velocity, is equal to A times T. It's equal to AT. And then we're just going to put our numbers in for this and solve for the change in velocity. So the acceleration is 21.3 meters per second squared. And the time period is 5. So it's multiplied by 5.35 seconds. And then we reach for our calculator and we come out with an answer of 113, so 113.955. Now, we need to put units on. We're looking at change of velocity, so the units are meters per second. Tommy threw a baseball high above his head, okay, and then he caught it. Yep, good on you, Tommy. Total flight time, 10 seconds, okay, grand. Acceleration due to gravity, okay, so just standard gravity on Earth. Now, we need to find out the speed that Tommy flung the ball into the air and the speed that it hit his hands again. All right, we're going to make an assumption for this one. The assumption is that the height above ground that Tommy released the ball from his hands is exactly the same as the height that he caught the ball. Now, by making this assumption, we can divvy up the total flight time. 5 seconds going up, 5 seconds coming down. And we need to do this because we actually do not have a way to determine directly the speed that the ball left Tommy's hand. What we can do is determine the speed that it hit Tommy's hands. Okay, so we can sort of do the second question first. So let's go with that. These speeds are going to be the same, of course, right? We're going up for 5 seconds, down for 5 seconds. And gravity is the same, right? So 9.81 downwards, okay? So the ball is slowing down on its way up. It's speeding up on its way back down. But at the top, right at the very top of the ball's flight, the ball is not actually moving. So if we wanted to work out the speed that he threw it up with, well, we know the final velocity for that top of the flight is 0, but we can't work out the initial velocity. But we're doing part B first, and we know the initial velocity is 0. So right up here, if we look at the coming down, the initial velocity equals 0, because when the ball was at the very top of its flight path, its vertical motion was temporarily 0, and then it accelerated back down towards the ground. So we're kind of actually doing part B first. So what we have in terms of an equation is V equals U plus AT. Now, of course, U equals 0. So what we actually have then is 0 plus the acceleration due to gravity is 9.81, and that's multiplied by the time. Now we're only looking at half of the total flight time, so we're multiplying it by 5. So now we have a nice simple calculation. We reach for our calculator. The 0 we don't even care about. 5 times 9.81. And it's going to come out at 49.05. Now this is velocity or speed, so we're looking at meters per second. That is the speed that the ball hit Tommy's hands, right? So we did the second part first. But that is actually also the speed that it left Tommy's hands. He threw it up at just over 49 meters per second. It slowed down, temporarily stopped, and then accelerated back down towards the ground. And he caught it when it was traveling at 49.05 meters per second. So it's actually the same answer for both parts of this question. Right, so Tiffany drops a rock. Okay, good on you, Tiff. She dropped it off a cliff. It hit the water with a certain speed. It took a certain time to get there. What was the acceleration of the rock, and what was the rock's average velocity? Well, straight away, we can assume that this is on Earth, and we know that acceleration is equal to 9.81 meters per second squared. First question done, except no, it's not really. We actually need to use an equation to determine this. We know what it should be. We should have an acceleration of 9.81 meters per second squared. But let's use our kinematics equations and find out what it actually was in this case. So let's just get rid of that. That's the initial conclusion that we may have jumped to. Oh, I know that one, 9.81. Let's just actually determine what it was. So we've got a kinematics equation for this. A equals V minus U over T. And then we simply put our numbers into this equation. So the velocity that it hit the water below, question tells us 73.8 meters per second. Great. She dropped the rock, so the initial velocity was actually 0, so U is 0. It wasn't actually falling until she opened her fingers, and then it started to accelerate, but it had 0 vertical velocity right at the start. And then we divide that by, there we go, a full line. We divide that by the time taken, which the question tells us was 7.53 seconds. Right. And now the next step is, of course, to reach for our calculator. And if we do this problem, we come out at 9.8. So far, so good. We wanted it to be 9.81 because that's gravity on Earth. Now, the answer isn't exactly that. It's 9.801 units, meters per second squared. Now, this has actually been rounded. So we also have to show any rounding. So I've rounded this to 3dp. 3dp just says 3 decimal places. It's a way to show that I've rounded this number to the third decimal place. Now, that's actually not what we said at the start. At the start, we said, oh, well, gravity on Earth should be 9.81. And this isn't. It's pretty close. So we're happy with this. What we need to remember is, we live in the real world, and in the real world, things aren't perfect. And maybe Tiffany on her stopwatch got the timing a little bit off, and it wasn't exactly 7.53 seconds, something like that, right? So, but we know that it should be about 9.81, and sure enough, it is. So, we're on the right track here. Now, the second part, calculate the rock's average velocity. Okay, well, that's fine because we have a kinematics equation for that one as well. The average velocity is the distance, or really the displacement, divided by the time. No problem. Except that there kind of is, because we don't know the distance. We don't know the height of the cliff. We don't know how high she actually dropped the rock from. So before we can do the second part of the question, work out the average velocity, we're going to have to go and find what the actual distance was. So this is the second part of the question is actually in 2 parts itself, because before we can do the average velocity, we're going to have to work out what was the displacement. So we've got D equals UT plus half AT squared. That 2 didn't work. That's better. Now this equation is actually a really nice one because often is the case, like this one, where that UT isn't actually going to be involved, because she dropped it. The initial velocity, vertical velocity, was 0. So that UT we can just get rid of, because if the U is 0, then UT is also equal to 0. So we're not actually going to add anything to our half AT squared. So the UT it's gone, and we're left with half AT squared. Well, we determined the acceleration in the first part of the question. It was 9.801. However, what you need to keep in mind is we're not going to write 9.801. We're going to write 9.800796813. What the heck? Where did that come from? Well, that was the actual answer that we got in the first part of the question. Right, 9.801 had been rounded to 3 decimal places. Now, what we don't do is use a rounded number in a further calculation. So instead of using 9.801, I'm actually using the full entire number that my calculator gave me. And then I'm going to multiply that by the square of the time. So the time was 7.53, but this is, of course, squared. And we're times that by half, so times half, same as divide by 2. Right, now we can reach for our calculator and get our new answer. And our answer for this is 277.857, and it's distance or displacement, so the units are meters. Lovely. Now that didn't actually answer the question that we need to find, but it did find us the height that the rock fell. So now we can come back to our average velocity equation, because now we know what d is. We just determined that. So now we can put that number in, 277.857, and divide that, of course, by the time taken for the rock to fall to the water. What was that? 7.53. And that comes out with an average velocity of 36.9 meters per second. So there we go. Now we've answered the second part of the question. It's just that we kind of had to go off to the side and work out what the displacement was first, how far the rock actually fell. During the filming of a disaster movie, a stunt woman leaps off a building. Okay, better her than me. And luckily for her, there was a safety net 125 meters below. Okay, grand. How long will she be in free fall? All right, this is pretty straightforward because we've got this nice little equation, d equals ut plus half at squared. Now, the reason this is a nice little equation is that her initial velocity was 0. So we could say u equals 0, and therefore we can get rid of ut. So therefore d equals half at squared, because of this key part here. U equals 0, so ut equals 0, so that makes our equation noticeably smaller. And we can rearrange this. So if that's what d is equal, well, this implies that t is equal to, and then we just rearrange the equation. So the 2 goes across, the half, I should say, the times half, or the divided by 2, different ways to talk about the same thing, that goes across the equals, and when we go across the equals, we have to do the opposite. So divide by 2 on the other side becomes a times by 2. The a multiplied by a, when the a is taken across the equal sign, it becomes divided by a. And of course, to get rid of the squared, we don't want t squared, we just want t. So we take the square root to get rid of t squared and just leave us at t. So then we, of course, put our numbers into the equation. So we've got the square root of 2 times. And now we actually go back and look at the question. The distance was 125. There we go. And we divide this by the acceleration. Well, we're assuming this is on Earth, so let's take 9.81. This will give us the time, and so we calculate this, and she actually fell for 5.05 seconds. Now, she didn't actually fall for exactly 5.05 seconds. This has been rounded, so of course we have to show our rounding. In this case, I went to 2 decimal places, so it's 2 dp, says 2 decimal places that answer has been rounded to. Now, this stunt woman, when she leaped off the building, she passed a camera. Okay, 35 meters below. What was her speed as she passes the camera? Right, so different equation this time. We have v squared is equal to u squared plus 2ad. Now, just like in the previous example, we can say u equals 0, so that will cancel out of this equation. It's just not going to be there. So this says that v squared is actually equal to 2ad, right? Because u equals 0. Now, we don't want v squared, we just want v, so this implies that v is equal to the square root. To get rid of the squared, we just take the square root. So square root of 2ad is our final equation to work this part out, which is equal to square root of 2 times, now gravity, acceleration due to gravity, I should say, is 9.81 meters per second squared, and the displacement, the distance that she fell down, was 35 meters, because that's how far below her the camera was at the window ledge. And this comes out with velocity downwards, speed downwards, of 26.205. As she passed the camera, she was traveling at just over 26 meters per second. Now, this number has been rounded, so as per usual, we show how far we have rounded. There we go. That's how fast she was traveling as she passed the camera, 35 meters below. Right, so she passed the camera, and then the camera actually tracked her for the rest of the fall down to the net. Okay, cool. How many seconds of film does the camera use? Well, a bit old school, we're using film. Okay, that's fine. Right, let's start with an equation. That's what we generally do. We start with an equation, we rearrange it if we need to, then we put the numbers in, and we reach for a calculator, get our answer, put the units on, and show any rounding. So, right, these are the steps we should be going. So we start with an equation. Great, we're looking for time, so let's rearrange this equation. So a equals v minus u over t, therefore t is equal to v minus u over a. So I've rearranged the equation. Now, what have we got here? We're going to have to do this in two parts, because we know the speed that she was traveling as she passed the camera. So we can work out how long she took to get down to there, and we know the total time, so we can work out how much time was remaining. All right, so let's do that. So the time that it took her to reach the camera, to reach a drop of 35 meters down, her speed, we just worked that out in the previous one, the 26.205, but of course that was a rounded number, and we're not going to use that rounded number, are we? No, we are not. We're going to use the full number that the calculator showed us, so 26.20, and so instead of 5, it was actually 496,136. Great. Minus u, well, that was her initial velocity. She had no vertical velocity as she started her fall, so minus 0. Which, you could think, oh, I won't even bother putting the minus 0 in because it's not going to do anything. But we really should show our working. The equation says v minus u, so we've got a number minus a number. So let's just put it in, even though the number is 0 there. And this is divided by the acceleration, which was 9.81. So this comes out at 2.6712 for, where am I up to? 9.884 seconds. Now this is the time that it took her to reach the 35 meters. Now you'll note I haven't bothered rounding this because it's not my final answer. So the film remaining, well, we have to remember what the total time taken was, and it was that 5.05 seconds, but that was the rounded number. So it's not exactly 5.05. We're going to use what our calculator showed us, right? So let's just split this off from our final answer. So we could say film records the remaining time. Film records time of the total time it took her to fall, which was 5.048187773. So in the first part of this whole problem, we worked out the time that she fell for was 5.05 seconds to 2 decimal places, but we used the full number. So that was the total flight time minus the time that it took her to reach the camera, which we've just calculated over to the left. So 2.6712498884. And that will leave us the time that she falls from 35 meters down to the net, which is essentially what the question is asking us. And that comes out at 2.38 seconds to 2 decimal places. There we go. So the film records the remaining time, which is another 2.38 seconds. Now, here we have a truck speeding along, going faster than it should, and it goes past a police officer who sets off after the truck and accelerates at this, and the truck was going at that. Right, how long did it take the officer to catch up with the truck? Well, we can use kinematics for this sort of problem too. Now, a problem like this might seem a little bit tricky. You just have to get your head around what's actually going on. Because we've got equations we can rearrange to find the time, no problem. Except, what have we got for the truck? Constant speed, and that's all. And what have we got for the officer? Well, we know the initial velocity, and we know the acceleration, but that doesn't allow us to find the time. Okay, so what we actually need to do for this one is to think of ourselves, all right, here's a truck booging along this way. Here is a police officer on a motorbike. I really don't know what I'm drawing here. There we go, police officer on a motorbike. When the truck goes past the police officer speeds off and catches up to the truck after a certain distance and after a certain time, right? So we had the truck's average speed was 72. Now, that's 72 kilometers per hour. So there's our first step, is to actually change that into meters per second. So we take our 72, we divide it by 3.6, and we come out at 20 meters per second. In terms of the police officer, we have an acceleration of, what's the police officer doing? 1.83 meters per second squared. So this is what we have, and we need to find this time, the time in here. From when that time in that section, from when the truck passes the police officer until the police officer catches up. Right, so we're actually going to combine two different equations. Here's how we would go doing a problem like this. We would talk about the distance that the police officer has to travel, and we want to make that the same as the distance that the truck travels. Okay, and once we've got this distance, then we can rearrange and find some times, right? So, two different equations. Well, we've got a very simple one for the truck. It's going at a constant speed, 72 kilometers per hour. So that's the average speed equals the distance over time, or displacement over time, when we're talking velocity. So we can say that d for the truck is equal to the average velocity times the time. Okay, so we've just taken our v av equals d over t, and we've rearranged it. So the t is not there anymore, it's over on this side. All right, so that's the truck side. And now we do a similar thing for the police officer side. So let's take the d equals ut plus half at squared. And we remember that the police officer was stationary. So u equals 0, so ut equals 0. So that equation comes down to simply half at squared. Okay, so remember technically it is ut plus half at squared, but initial velocity of 0 means we can negate that part of the equation. That part that was added on, let's just not even worry about it. Okay, so might look a little bit complex, but now we've got t's that we can work out because we know the acceleration and we know the average velocity. So we just have one unknown now. The unknown is the t. So now we just solve for t. Let's take this one across to the other side of the equals, and that will cancel out this squared because we'll be dividing by t. And we'll take the a across this side of the equals. So when all said and done, what we have is that t is now equal to 2 times the average velocity divided by the acceleration. And this we can now solve for this first part of the problem. So there's our rearranged equation. We now plug in our numbers. 2 times the average velocity was 20. Remember, I know the question said 72, but that was kilometers per hour, which is equal to 20 meters per second. And we divide that by the police officer's acceleration, which is 1.83. Now we reach for our calculator and we come over here because I ran out of room. And that is equal to 21.86 seconds. That's how long it takes the police officer to catch up to the truck. That has been rounded actually to 2 decimal places, so we need to state that. So there we go. How long did it take the officer to catch up with the truck? It took 21.86 seconds, roughly, right? Rounded to 2 dp anyway. Alrighty. Now we have another part to this question. How far did the truck travel in this time? Well, we've actually done the tricky part. Just getting our head around what's going on and realizing that, oh, wait, we need an equation from the officer to match an equation from the truck in terms of the distance. So we've got our 2 equations and we combine them and then we rearrange to find t. That was actually the tricky part because now we're just asked for the distance that the truck traveled. Well, that's okay because we have the average velocity is equal to d over t. We just rearrange this. This implies that d is equal to the average velocity times t, times the time. So the question told us 20, well, again, told us 72, but we know it's actually 20 in terms of meters per second. And the time we just calculated in the previous part of this question was 21.86 seconds, except it wasn't quite, was it? No, what it was, according to the calculator, was 21. Wasn't 0.86, it was 0.85, but then it had been rounded, so that 5 rounded up to the 6, but it was 0.857923. Oh, that 3 didn't work out. Let's try that again. There we go. So that's what the time actually worked out as. That was the calculator answer, and we don't use a rounded number in a further calculation, so you have to use the full time there. And the distance works out to be 437 and a little bit, 0.16 meters, rounded to 2 dp. There we go. So that was quite a very basic equation, actually. So that part, not too tricky at all. Like I said, we've already actually done the tricky part in part A, just sort of working out what's going on and how we would go about solving part A. That was really the tricky part of this question. So that's how far the truck traveled in that time. Right, final part of this question, this problem set. How fast was the officer going when they passed the truck? Right, just like part B, which is a fairly straightforward one, so is this, because we have all the data we need, and it's simply a matter of plugging it into our equation. Our equation in this case is going to, that didn't work out very well. Our equation is going to be V equals U plus AT. Now, of course, the officer was stationary at the start, so U, the initial velocity, is 0. We're not actually going to add anything on. The acceleration, the question tells us, 1.83, multiplied by the time. Now, the time was what we've just used in the previous part, 21.8579. Oh, goodness, what's wrong with my pen at the moment? 79.235. So once again, we're using the entire number that the calculator had previously given us for time. We're not using that initial 21.86 that we said for part A that was rounded, and we're not going to use a rounded number in a further calculation. So we reach for our calculator and we get an answer of 40 meters per second. So there you go. Like part B, that one was quite a straightforward one. We had an equation, put the numbers in, got the answer, no problem. The real tricky part for this question set was just really in part A, working out what's going on and how to solve part A there for the time.
And that's how it's done.
Yeah, boy, what he said.